Hello, welcome back to Algebra. The title of this lesson is Solving Systems of Linear Equations in Three Variables, or with Three Variables, with Substitution, Part 1. So it's a very lengthy, very complex sounding title. The basic idea is we have learned already how to solve linear systems of equations before. We did that a long time ago when we had two lines. Remember, linear means line, right? Or something that doesn't curve. So two lines, of course, can intersect and they can have a crossing point, and we found those solutions by substitution. We also did addition, and we also used graphing back then. With two lines, it's very easy to graph things and know what's going on, but whenever you have three variables, x, y, and z, then it gets difficult because the math to find the solution it's more involved. And also, it's a lot more involved to visualize what's happening. With a line, it's very simple. Two lines either cross or they don't. If they cross, there's an intersection point, and we find it, that's the solution. But if they're parallel, it means they don't cross, then there's no solution. Those are very simple cases. But when you have three variables, x, y, and z, then the graphs become hard to graph. You can't really graph them so easily, and it's hard to visualize what's going on. So in this lesson, what we're going to do is introduce what a system of equations in three dimensions looks like as far as the math goes. We're going to sketch some pictures so you'll understand kind of what's going on in terms of what their graphs would look like, kind of. And then we're going to solve a problem at the end to show you how to actually figure out what the solution to a system like that looks like. All right, so let's crawl before we can walk. Let's go back down memory lane, down to a system of linear equations with only two variables, x and y, and we'll extend that to talk about what happens now that we have three variables called z, the third variable called z. And also I'd like to say, if you haven't already watched my last lesson, please do it now. In the last lesson, I told you all about 3D graphing, 3D points, and 3D functions. So if you haven't already looked at that, then it's going to seem confusing here, but I've already talked about the fundamental basics of what you need to understand to be with me here. So what we're going to do is talk about a system of equations in 2D. So we're going to call this a linear system. That's what SYS means. A linear system in two dimensions. Two dimensions means x and y, so they're basically going to be lines. Lines means linear. Okay. So what would an example system like that look like? Well, it might have something like this. 2x plus y is equal to 3. And the other equation might be x minus 3y is equal to -1. Now, this is a system of equations because there's two equations. There's also two unknowns, x and y. So what you're really trying to do is figure out what value of x and y will both satisfy both equations at the same exact time. That's going to be the intersection point. Now, what do the graphs of these things look like? I mean, I'm not a computer. I don't know exactly what they look like, but I know that they're lines. And you should know that they're lines too. And the reason that you know that they're lines and not some kind of crazy curved kind of graph is because if I wanted to, I could solve the top equation and put it into y is equal to mx plus b form. How do I know I could do that? Well, because this is y, I could subtract the 2x, it would be -2x plus 3, that's mx plus b. And I could look at the slope and the y-intercept. This means this is a line. Some kind of line. In other words, it's not a parabola. It doesn't curve. It's not an ellipse. It's not a hyperbola. It's not a cubic function. It's not a quartic function. It's not a square root radical function. It's not an exponential function. It's none of those. It has to be a line because of the simple nature of the way the variables just have coefficients in front. Now this equation, same sort of thing. If I wanted to, I could solve it and put it in mx plus b form. Because I could take the x and move it over there. I could divide by 3. I'd have some fractions, but it would still be mx plus b, which is a line. So anytime you have number times x plus number times y equals number times x plus number times y equals number, then you automatically know it's a line. These are two lines. That's how you know that. Now, if you were to have an x squared running around, then you would know it's not a line. If a y squared is running around, you would know it's not a line. If there's a radical anywhere on a variable, like a square root or a cube root or something, you would know it's not a line. Those are what the things to look for. Think back to all the ellipses we graphed, all the circles we graphed. They always have squares everywhere. So you know those aren't lines, but these are lines. That's why it's a linear system of equations. Also notice, if there's two variables, in this case x and y, only way to solve that system for x and y is to have two equations. You have to have the same number of equations as you do variables, otherwise you can't solve it. So we have two equations, x and y. We have two variables, so that means this set of equations is solvable. Okay? And we're not going to solve it because we've done it many times in the past. We've had entire lessons on this. But you know that this is a line and this is a line. So what's in general going to happen is these lines are going to cross somewhere, probably. They may or may not, but they probably will cross somewhere. And this intersection point, this single intersection point, is called the solution. Specifically, there's only one solution. Because the solution is the crossing point. It's the point that's common to both lines. It satisfies both equations. And so you say that it has one point in common with each of the equations, right? That's what that means. Now, of course, lines do not have to intersect. You could have a system of equations where I have a line going up like this and a line exactly parallel to it. Now, I can't draw exactly parallel, but you have to pretend these are exactly parallel. And if these actually are the two lines that you have, these are parallel lines, which means there's no solution. The word solution in your mind, you need to replace with intersection points, points in common between the two graphs. That's what you're looking for. That's what a solution is. It's a common point between two graphs, right? But if the lines are parallel, then I could go 65 million light years away and they'll still never cross. There's never any crossing points for parallel lines, but if they're ever so slightly not parallel, eventually they will cross. Maybe it's 10 million light years away, but they will cross somewhere, and the solution's way, way, way down there. Okay, so this is a system of equations in two dimensions. We need two equations. We have two variables. We know how to solve these systems. All right, and first we solved them by graphing, and then we solved them by substitution, and we solved them by what we called addition. Okay, so what we want to do now is talk about what does a system of equations look like in three dimensions, and not only what does it look like as far as the math, but what does it look like in terms of physically? If we try to graph it, what does it look like, and what kind of solutions can we have for a system of equations in three dimensions? So let's take a look at that. What if we have a linear system of equations in three dimensions? What does that look like? Well, up here we had something times x plus something times y is equal to a number for all of those. So here we might have a system that looks like this. 2x plus y plus z is equal to a number. Notice the form of this equation is exactly the same as the form of this one. It's something times x plus something times y plus now we have something new, something times z is equal to a number. It's exactly the same form. It just has a new variable in it. All right, so I can have another equation underneath it, 3x plus 2y minus z is equal to negative 2. That's another equation there in the system. And then I have a third equation, let's say negative x minus y plus 6 times z is equal to 10. So I have three equations. Notice up here I had two equations and two unknowns. That allows me to solve this system. Notice here I have three equations, and I also have three unknowns, x and y and z. So because I have three variables, I must have three equations to solve it. That is something that's true of any kind of system of equations in algebra. If you only have two variables, you need two equations to solve it. If you have three equations, you need three variables to solve it. If you have four variables, then you need four equations to solve it. If you're working in quantum mechanics in 11 dimensions, right, then you have 11 variables, you need 11 equations to solve it. If you have 65 variables, which sometimes actually happens, believe it or not, for very complex problems with electric fields and all kinds of weird configurations in different directions, 65 variables, you need 65 equations to solve it. That's why predicting the weather is so hard. People say, why can't we predict the weather? The weather's no big deal. Well, the weather's one of the most complex systems we have on the planet because every point in space has a pressure, it has a temperature, it has a velocity because the air is moving, and there's also other things like there's heating coming in from the sun, there's all kinds of other effects I don't want to get into. There's tons of effects that come into play for every point, and there's almost an infinite number of points, and all of those points influence all of their neighboring points. So there's tons of variables, and so because of that you need tons of equations. So in order to really solve the weather systems, you have to have computers to crunch through all of those equations. Now we only have three equations and three unknowns, but for something really complex you might need 1,000 equations. Seriously. And when you get into gravity and black holes, you could easily have thousands of equations to solve what's going on near a black hole with thousands of variables, right? It's true. So we have three variables, we have three equations. Now the question is, if these things look like lines, what do these things look like? So these things can't look like lines, but when you have three variables like that, and they're linear, meaning there's no squares, no terms have squares anywhere, these do not look like lines, these look like planes. When you think about it, this pencil is a line. It just goes like this. if you take and stretch this thing in the other dimension, then this line then becomes a plane. It's still kind of flat. There's no curviness to it. There's no beautiful like elliptical shape or anything. It's still flat. It's just flat in another dimension other than this one. It goes this way and it goes this way, but it's flat. So these things are lines, these things are planes. You kind of have to kind of take my word for it a little bit because these are lines and this is by extension, these are planes. But you can convince yourself of that if you were to plot them. I'm not going to plot them. It would take too much time for us to plot them. But for instance, one way in which you could do that is you could solve this equation for z. And you could solve this for z and solve this for z. And then you could have an equation in terms of z as a function of x and y. And we talked about that in the last lesson. So for instance, here is the x direction. Here's the y direction. Here is the z direction. Let's pretend I'm not going to use these equations right here. Let's say that I solved for some other equation of z, and it came out to be something like this. Let's say it was x plus 2y minus 4. Notice that if I solve for z, I'm going to take and move these numbers over to the other side. So I could have used this equation. I just didn't. You know, negative 2y, negative 2x minus y plus 1, whatever. You can see there's a number in front of x, a number in front of y, and a constant. If I move these over, there's going to be a number in front of x, a number in front of y, and a constant. And z is what's equal to over here. So z is a function of x and y. That means I stick x values in and I stick y values in and I calculate the value, the height, the value of z, like this. And because there's no squares anywhere, if you actually made a table of values and put values of x and values of y and calculated values of z, what you would figure out is that for like a given value of x, right, over here, and a given value of y, so an x value and a y value, right, you would get some value of z. And when you, so let's say 3 for x and 4 for y, you would calculate, this would give you a value of z for like 7 or something. I'm just making it up, right? But then if you did it for more and more and more points, what would end up happening, you would find, is that this is going to form a plane. It would form a plane. In other words, it would form a surface in three-dimensional space where the x and y plane is underneath it. I take little points, I calculate the value of z, and that's going to give me the height. Now, the plane might be tilted like this, or the plane might be tilted like this, or the plane might be tilted like this or like this. You see, the plane can go any which way, just like when you have lines up here. Lines can be any which way also. But when you have a third dimension, the plane can be pointed any which way you want. And that's why it's almost impossible to graph these things on paper. But you can put them into computers and see beautiful pictures like that. I'm just showing you that if you have equations that has something times x plus something times y plus something times z is equal to a number, and there's no squares anywhere, no radicals, nothing crazy, just the linear things, it's always going to look like this if you solve for z. Something like this, and that's always going to yield a plane, which is just a line which has been stretched in another direction. So you have to accept for a minute that these linear systems of equations are always going to form planes. They're always going to look like planes. You cannot predict by looking at them how they're going to be oriented, but they will always form planes. All right? So because they can form planes, the way that these things make solutions is difficult to predict because this is a plane. This equation represents some plane somehow in space. This is a separate equation that forms some different plane somehow in space. This third equation is yet a third plane oriented somehow in space. So how do we find solutions? What do solutions look like for three planes that intersect like this? Because up here it was easy. For lines, they intersect. Bam, there's the point. It's easy to see. Oh, they're parallel. Okay, there's no solution. Okay, so how do they look when you have planes, three planes? What do the solutions look like? So it's going to get cumbersome here, but I'm going to try to use a prop, okay, because it's the best I can do. Let me see if I can put this down here. There's a couple of different cases we need to look at, all right? The first case, if you go back to linear systems of lines, we had the parallel line case when there was no solution. So it is possible when you have three planes like this to have no solution. Sometimes you're going to solve the system of equations and there's not going to be any solution at all. What do you think that means? If there's no solution, that means that the planes never intersect each other. But it means they never intersect at a common point because remember, a solution is a common point between all three. So if this is a plane and this is a plane, and this is a plane. I don't have three hands, unfortunately, but if you can visualize, this is a plane coming to you. The yellow plane is coming parallel, exactly parallel to this one, and the third plane is also exactly parallel. Maybe they're like this, maybe they're angled like this, but they're all parallel. Then they never intersect. Those planes will never have a common point, so they'll never have a solution. So no intersection. If I can spell intersection, which means you have parallel. That's what that means, planes. So basically, how do you draw that? How do I draw that on, on a board? I don't know. You could say, here's a plane, here's a plane, here's a plane. I'm drawing them as lines. This is a top view. In other words, you have to use your imagination, but this is a plane right here, then this is a plane right here, then this is a plane right here, and you're looking down on them. Plane, plane, plane. They never intersect, so there's no solution. So that's one way that you can get no solution. All right, and then what is the other thing that you can have? You can have no solution. Let me see, we'll check my notes here. You can have no solution. They don't have to be parallel to have no solution. They can also have no solution if they just don't intersect at a common point. So let's take a look at another example of this. What if I had one plane that went over like this, looking again down, like one plane that's like this, and then another plane that intersects it like this, but then the third plane goes like this. So you see I have three planes. I have one plane like this, one plane like this, and one plane like this. But you see, I do have two of the planes intersecting, and two of the planes intersecting, and two of the planes intersecting, but they never all three intersect at the same spot, right? So here's a plane, right? I can't do this without being crazy awkward. There's an intersection point between planes, right? But then the third one intersects the other two, but never at the same spot, because a solution has to be common to all three of them. So there's no point here that's common to all three of them, like this. You could also have a plane like this, a plane like this, a plane like this. So yes, you have intersection points between two of the three, but never among all three. So it's very common to have no solution for planes because it's very easy to have them oriented where they're not all going in the same spot. Okay? Now, you can also have an interesting case where you have infinite solutions. All right, and it's going to be a little bit easier for me to gesture this by pretending that one of the planes is actually the chalkboard, the board here. So pretend that one of the three planes is actually this board right here. If I take another plane and intersect it, then you can see that what's going to happen, just with these two planes, you got to pretend that this yellow plane is going through and intersecting. You see, there's an infinite number of points here that are common to both of this plane. This plane is here and this plane is right here. There's an infinity number of points right here that are common to this. So then if I take my third plane, let's say here's one of the three planes, here's one of the three planes, here's one of the three planes, and it intersects exactly on this line. You see, this one also goes through the board, this one also goes through the board, and they go through at exactly the same spot. There's an infinity number of points right along this line that's common to this plane, and also to this plane, all at the same spot. And there's an infinite number of them. So if you wanted to draw that, it's very difficult. But from a top view, you could say you had one plane, here's another plane, and the third plane goes right through top view, looking down on the planes. It looks like a single point, but really these are all planes. So this thing forms a line that goes down there, and that's why there's an infinite number of points. So sometimes you'll solve your system of equations in 3 dimensions, and you won't get a single answer. You'll actually get an infinity of answers. And that's because the three planes came together in such a way that they all just kind of found one infinity of one line, which forms an infinite number of points, like this. Now, finally, I saved the best for last. There is a way in which you can have one single solution. You can also have one solution. Right? Now, again, it's going to be easier for you to pretend that the board is one of these planes. What if the board was one of the three planes, and then I have one of this guy coming in like this. So you see, if I have him going through, this forms an infinity of commonality between them. But then if I take this one, and it's really hard to do because I can't cut through, but what if I have this plane going through like this as well, cutting through the orange one and cutting through the board down here. So you see what's going to happen is this is an infinity number of points, but once this one slices through, there's only going to be one point where all of them kind of touch right in the middle. I can try my best to draw it, but it's going to be different. Difficult. Let's say I have a plane here and a plane here. I'm looking at a top view. So there's an intersection point, plane here and a plane here, just like this, and this forms a line of infinite solutions. But then the third plane is actually kind of like perpendicular to those. So in other words, it's a flat board and you have these two planes cutting through it. So even though it would have been a line of infinite points, it cuts through a board. And so there's really only one point right here in the center where everything crosses crisscross and the other one cuts through one point. One solution. It's a single point. It would be like x, comma, y, comma, z. It would be some number, and that would be the single solution. So again, it's difficult because everything's in 3 dimensions and it's very hard to gesture, but you can very easily have no solutions if you have 3 parallel planes, or if the 3 planes cut in such a way that they don't all go in the same, cut in the same exact location. That's going to give you no solution at all. Or if they cut through each other where they all go through a common line, then you have an infinity of solutions common to both. Or if you have 2 that form kind of a line of solutions and have the third one slice through that, then you're only going to have one point right at the intersection of all 3 of them. That's going to form a single point, x, comma, y, comma, z. That's going to be your solution. So what we need to do now is keep this in the back of our mind while we solve our first set of equations. Because the type of solution you get is going to be one of these, essentially. So our first system is going to look like this. Let's say we have 2x plus 3y plus 2z is equal to 13. The next equation is 2y plus z is equal to 1. And the third equation is z is equal to 3. So you might say this does not look like you told me it would look. You said it would look like this. But notice this is something times x plus something times y plus something times z is equal to a number. Something times x plus something times y plus something times z is equal to a number. Same thing for here. Here it's the same thing. It's still something times x, it's just 0. And then something times y and something times z. For this one, it's still something times x, it happens to be 0x, 0y, and something times z. So you see all of these still form planes. It's just that some of the variables are set equal to 0. So they all still form 3 planes in a space, and they're all going to intersect in some kind of way. Now I want to point out to you that the shape of this thing kind of looks like a triangle. Like this. Notice it's got a pointy in here, goes down like this. This is called triangle form. When a system of equations, and 3 variables, in general, a system of equations, let me just back up for a second. If you wanted to solve this thing by substitution, you can definitely do it, but it's very hard to do. It's not crazy hard, it's just a lot of work on the paper to do it. Why is that the case? Because if I wanted to solve this by substitution, I have to pick 2 equations to solve for different variables and then substitute it into the third one. So I could solve this one for x. X is equal to some junk. And then I would have to pick this one and solve for y. Y is equal to some junk. I'll move everything over. Once I have x and y, I take both of them and put them into here. And then I'm going to have and be able to solve for something, and then I have to back substitute several times. And so you're taking 2 equations, solving for different things, you're plugging in, you're rearranging, you're plugging in again, and it's kind of a spaghetti mess, okay? If your system of equations already looks like this, it's much, much easier to solve. And let's look at why that is the case. We call this triangular form. It makes it easy to solve. Why? Because then I can just take the z value, which is already given to me, and I can plug it in directly into the equation above. I don't want to put it into this one. If I do put it into this one, that's fine, but I have x and y, which are still unknown, and I cannot solve for them. But if I put it into here, then I can solve for something. So the way I do that is I say 2 times y plus z, but now no, z is equal to 3 is 1. I just take and plug it into that second equation. 2y is equal to, subtract, I get negative 2. Y is equal to negative 1. So now I know that y is equal to a number. It's one of the three numbers I need. I need x, I need y, and I need z. And actually, I know what z is equal to, and now I know what y is equal to. So actually, all I need is to know what x is equal to. How do you think I figured that out? Well, now I know what z is. Now I know what y is. I take both of those and stick them back in here. So what I do is I plug in y is equal to -1 and z is equal to 3 into the following equation, the big one at the top. 2x plus 3y plus 2z is equal to 13. I just stick these values in. So I get 2x plus 3 times y, which is -1, plus 2 times z, which is 3, is 13. So I have 2x, this becomes -3, this becomes 6, like this. I add these together, 2x plus 3, add these together, get 3, is equal to 13. And now I subtract. 13 minus the 3 is 10, and then I divide by 2, and I get 5. So I get x is equal to 5. So now I know x is 5, and y is -1, and z is equal to 3. So now I can write my solution. It's going to be only one solution. It's this one point that I've found. The x value was 5, the y value was -1, and the z value was 3. And this is, of course, x, comma, y, comma, z. Let me double check myself, 5, comma, -1, comma, 3. All right? Now, this was so easy to solve because the system was already in what we call triangle form. Triangle form is really easy because it basically means that one of the variables is already given to you, essentially. You take that single variable that was given to you and you put it into the next bigger equation right above. And because it's a triangle, if you stick it in here, you're always going to be able to find the next variable. Once you have those two, you stick them both into the triangle above. So you kind of work above, up and up and up like this, eventually getting to where you find that third variable. Now this system of equations is not in triangle form. So what we're going to do is we solve these, is we're going to get a little more practice with solving these in triangular form to make sure you kind of get a little more practice with what I just showed you here. And then we're going to do these kinds of equations here, where the system is not in triangular form like this. But guess what we're going to do? We're going to learn a technique to take this system and put it into triangular form. We're going to be able to take any system like this and manipulate it so that it always looks like a triangle like this. So then we can do the easy solution method. Now, if you look at other algebra books, even the ones I learned on way back in the day, we may have learned this, maybe we didn't, maybe we did, but we learned other ways to solve these systems. But almost all the other ways are actually way more cumbersome. Trying to substitute, backward substitute all these different ways, trying to add them and eliminate everything all at once, it's very, very difficult to do. The way that we're going to learn it here is bulletproof and it works for everything. If it's already in triangular form, do this method and it works every time. If it's not in triangular form, we're going to manipulate it to put it into triangular form, and then we're going to do the same technique, and we'll get the solution correct every single time with a minimum of heartburn. So we did a lot in this lesson. We learned about the concept of linear systems in two dimensions. They form lines. Either they intersect and they have one solution, or they're parallel and they have no solutions. A linear system in 3 dimensions do not form lines, they form planes. 3 planes, which can be oriented and intersect in very weird and interesting kind of ways. You can have them not intersect at all, or intersect in ways where they don't all come together at once, and that has actually no commonality among all 3, so there's no solution. Or they can intersect in such a way that they form an infinity of solutions that run along the intersection line, so you have an infinite solution. This is also called, by the way, a dependent set of equations. It's called dependent set of equations when you have infinite solutions like that. Or you can just simply have one point as a solution, where you have a plane where 2 more planes kind of crisscross and go into it, so you only have 1 point. And that is the exact kind of solution that we had, or the type of system that we had here, where we had 1 point. You cannot figure out by looking at your system if it's going to have 1 solution, no solutions, or infinite solutions. You have to try to solve it. So follow me on to the next lesson after you have practiced this. We're going to get some more practice with solving these triangle systems by substitution, and then we'll work on the more general, more complex linear systems in 3 variables. As I mentioned, we're going to make them into triangular form before we solve them, so we'll work on that at the very last part. So make sure you can do this. Following on to the next lesson, we'll continue building your skills right now.